Okay, welcome back, everybody. I hope you enjoyed your break and the little snacks we had. Next up, we have Devon, who will talk to us about Unicode.
Hey guys, my name is Devon Peticolas, and I'm a data engineer, and we're going to talk about one of my all-time favorite subjects, which you guys are probably really bored by, hopefully not if you're at this talk, which is Unicode. And it's really not just about Unicode, but it's how and why we speak in Unicode. And I think this is because I personally find not just Unicode itself interesting, but I find the history of how we got to Unicode to be really interesting. So that's going to be a huge, heavy focus of this talk. So we're going to go over a lot about the history of Unicode. We're going to talk about some history of some older encodings and how we got up to where we are now. And then we're going to talk about how it works in Python 2.7 and how it works in Python 3 and the differences. And then finally, we're going to talk about some best practices. Does that go to the next slide? There we go. Wait, yep, there we go. Wait, no. One second. There we go. Okay, so you guys have probably seen this error message before. Unicode decode error ASCII codec can't be decode byte 0xC3 in position 6, ordinal not in range 128. And you've read it and you have no idea what it means. It is absolute nonsense. You've probably spent a bunch of time searching on Stack Overflow to figure out what this means. You've sat there and encoded and then decoded and tried Latin 1, and then you kind of play this whack-a-mole back and forth, and you really had no idea what's going on. I know you have. I've done it too. And that's because you didn't really get what's going on in this error message. And I'm here to tell you that this error message is not only really informative and helpful, but it actually tells the story of encoding. It goes way back, and it's really interesting to see how we got here. So we start back at the very beginning with Morse code. And this seems like a crazy point to start, but it's really important to think about how we got here. And so this is 1863. Samuel Morse invents the telegraph, which basically lets us create signal over a wire and send a message to the other side of the world. And when we're doing this, this is the first time anyone ever actually worries about the idea of encoding language or some sort of written language or spoken language into some sort of electrical form. And so the solution to how this is going to be done is something called Morse code. And so Morse code is the series of taking this set of letters and converting into dots and dashes, of the dash being a longer hold of signal, to send a message over a wire and actually over electricity. And so the thing to think about this here is that there's really two pieces of Morse code that are going on. There's the character set, which is all the characters that Morse code supports, which is the basic alphabet, no capitalization, just A through Z in the Latin alphabet. And it supports a number system, 1 through 9 and 0. And maybe a couple punctuation, but really not much else. And so that is really, so the character set is the list of characters recognized by the hardware. In this case, the hardware is a human being on either end who's listening and writing the message. The second half of it is the encoding. And so the encoding is the system at which we're converting the characters into this digital signal. And so it's a system of rules that converts a character to and from binary. And Morse code's not exactly binary, but it ends up acting something like binary when it goes over the wire. So this still works. And again, in this case, the encoding is basically just a human being who's learned and memorized this algorithm. And it's actually such an easy algorithm that you might have actually tried to write a Morse code encoder as a Python project once. It's really simple. You just have this map of letters that map to, a bunch of dots and dashes. And then you have a function that iterates over the string and converts each one of those into dots and dashes. And you can encode burrito into some series of dots and dashes. And the decode is the same thing. You just take the dots and dashes and you convert them back into letters. So this is the fundamentals of encoding and decoding back in the 1800s. And you might be thinking, like, why are we talking about this? This is, I know what Morse code is. What does this have to do with Unicode? But I'm here to tell you that basically we started with this and we eventually got to this. And the story of how we got there is really fundamental. The second big thing that happened was in 1874, we have Baudot code, which is, I probably said his name wrong, but this is Emile Baudot, and basically he looks at Morse code and he looks at what's happening right now, and he realizes that it's incredibly efficient. Most of the time, the wire is actually not being used. And what he identifies is that the biggest issue is the way that the characters are being spaced out. Basically, in Morse code, all of the really common characters are short, and all the less common characters are really long. But when you have this variable length character, there's additional pauses that are happening. There's a lot of just waiting. There's actually not that much being used. And he invents something that I really don't think anyone gives him credit for, which is a really big deal. He invents fixed width binary encoding. He creates a 5-bit system for encoding the entire alphabet. And he creates this really crazy contraption that involves this like 5-key keyboard where you use 2 fingers and you actually press 2 at the same time. So you enter a single character with 2 hands. And you have to do it on this regular cadence. And what's cool about this is that when you have a 5-bit encoding that's going over the wire, you can actually have multiple signals going over the wire at the same time that are spaced a little bit off from each other. And what he creates is, modern multiplexing, which is really crazy. You can actually have 4 people communicating a signal over the wire at the same time simultaneously. And this becomes a really big deal. And what's even crazier is, like, in the beginning, you have an operator who's still sitting there operating this machine. But by the end of the century, this has been improved to the point where now we're actually writing the 5-bit code to punch card before we submit it into the system. So this means that by 1900, we are encoding language into a binary form and writing it in a 5-bit binary form, writing it to punch card, and then sending it over a wire to control some printer on the other side of the world. And this is like 1900. And so actually this is, shortly after this is when we start seeing the very first control character. I'm also going to mess this up. It's retour de chariot. This is a French patent, I think. But this is the carriage return character, which is the enter key on your keyboard, released in 1901. So the enter key on your keyboard is 116 years old. So it's a really crazy idea to think about. And this is really a big thing because this is a control key. This is not something that's being printed out in the message. The original version of this stuff was printing out in ticker tape. This was actually saying, okay, machine printer, now make a new line, like, fit to this paper. And this is a big change for how things are working. So over the next 60 years, there's an enormous Cambian explosion of all these different encodings that start happening. Because as eventually people want to start to do this kind of stuff for not just communicating over to printing machines across a wire, they want to start using it for other systems. And what you end up seeing is that in different industries, different people are doing different things. So for example, in the military, the US military, people are using this thing called field data, which includes additional characters such as, additional addition and subtraction, weird stuff like that. The Western Union contains, an ampersand in their stuff. There's certain punch card systems that contain @ signs. And all of these don't really communicate with each other. They're all totally different standards, and it makes things kind of complicated. So the American Standards Association, which later becomes the American National Standards Institution, ANSI, at the time ASA, decides to take all of these standards and combine them. And at the time, they've actually evolved from being a 5-bit standard to everyone's now operating in 6-bit standards, including IBM is working on the 704, which is where they wrote Lisp and Fortran and a 6-bit encoding, which is a crazy thing to think about. So ASCII comes out, and ASCII is going to be the thing that's going to unify everyone together. And so they basically split up into 2 subcommittees. There's someone who goes to all the industries and says, in America at least, and says, okay, what printable characters do you need to use to make everything work? And another subcommittee that goes out and says, what control characters do you need? And the printable characters committee says, okay, we need the basic alphabet, A through Z. We need 0 through 9, and we need 26 special characters, like punctuation and white space and weird stuff like that. And then the control character committee goes out and comes back and says, we need 10 control characters to make all the different machines happy. And when they add them together, they realize they need 73 characters, which is just 9 too many to fit inside of a 6-bit code. So they make this kind of crazy decision to use a 7-bit standard. And this becomes ASCII. So you can see that 7-bit wide. And they also add this additional thing where they now have lowercase characters in here as well. And there's like a lot of really nice features of ASCII where, for example, the alphabet starts at 1 if you truncate off the leftmost bits. If you ignore this bit here, you can actually have case and sensitivity between the lowercase and the uppercase. But overall, it's like a pretty good standard. And there's this conversation that's had when they're releasing it, which is like, no one right now is using a 6-bit architecture, or a 7-bit architecture. Everyone's on 6-bit. So why are we doing 7 bits when we could just go all the way up to 8? Because that's the more realistic evolution for the future of computing. And they discuss this and they say, well, we don't have a reason to go to 8 bits. And this is slightly better compression, so we should keep it at 7 bits. And I'm sure someone will come up with something to do with the 8th bit in the future. Probably something really useful, and I'm sure we'll all agree on it. And this is, of course, the beginning of the end. So the 8th bit in the very beginning is used for a huge variety of things. Right off the bat, it's used for things like, so early in this time, there's 1-inch 8-track tape. So they can store in 8 bits, and they decide to use that 8th track with the 8th bit as a parity bit to do really basic error checking. So there should always be an even number of bits in every single character, for example. That tells if your tape is bad. Certain printers use the 8th bit to do things like italics, which is really kind of uninteresting. But the really big use case is that ASCII is becoming really popular among the Americans, and a lot of code's being written by the Americans. But for the rest of the world, everyone wants to be able to write in their own language. And so what we see is this giant explosion of different encoding types. So for example, this is Latin 1, which is pretty common. It was used for MySQL for quite a while, and it's a 1-byte encoding that contains a bunch of additional Latin characters. We also have Greek. Greek is a language that we communicate in 1 byte. There's Hebrew. There's a separate one for Hebrew. And there's this funny thing where, like, we can now write Hebrew and we can now write Greek, but we can't write Greek and Hebrew. And we also can't really effectively translate code that, or data that was written in Greek into data that was written in Hebrew or in a different encoding. Becomes kind of a problem. This is actually my favorite 1-byte encoding. I don't know if you guys recognize it. Does anyone know what that one is? This is the 1-byte coding used for the original Pokemon game. I love this encoding because there's actually a control character to print out Poke, so they can make the word Pokemon only 4 bytes. It's really great. So this is the problems that we're dealing with on, this side of the world. But on this side of the world, there's actually a lot more going on. So I don't know if you guys have ever been to Japan before. But in Japan, there's actually more than one writing system, and it's not the Latin one. So in Japan, you have 3 major writing systems. You have kanji, which is basically used for everything, and it's iconographic, so there's 1 character for every single word. There's hiragana, which is often used for pronunciations and inflections, and then there's katakana, which is generally used for foreign words and certain technical terms. And all 3 of these definitely do not fit in a single byte, let alone the extended 128 characters that you can get from extending ASCII. So there's this decision right off the bat that, and this is also, by the way, an example of a kanji typewriter, which you can't really see because it's kind of blurred out, but those are tons and tons of little tiny keys, each for different kanji. And so there's a decision by the Japanese industrial standard to settle on using katakana to start, because they can just make an extended ASCII using this, and they just basically take all the katakana and stuff it onto this extended ASCII space. And this is, for the most part, backwards compatible with ASCII. The one weird exception is that backslash is replaced by yen, which has forever plagued Stack Overflow for the rest of time, where there's Windows command prompts where people have yens in them. But for the most part, it's backwards compatible with ASCII, and it supports katakana, which is pretty cool. And most importantly, this massively improves the amount of cool ASCII art that you could do in Japan compared to us in the West. But so very quickly, there's this really quick explosion of new character sets that start happening, because clearly people want to write in more than just katakana. So in 1978, we see an extension with JISX 0208, which is considered kind of like the standard, and that adds in hiragana and kanji, and then JISX 02012, which adds even more kanji, and then 0213, which adds even more kanji. And this is just, remember, there's 2 things that we have to worry about. There's an encoding, and then there's a character set. So this is just the character set. And in ASCII and in 0201, this was actually really simple because these were just, 1 byte. It was easy to think about them at the same time. But as we start extending the character set, there starts to be this divide in the way that we're going to be doing the encoding. So if we look at, in the beginning, we had ASCII. And then we have 0201 follows up. And 0201 is backwards compatible with ASCII for the most part. And then we have basically 2 divides when we start to support 0208 with all the kanji, one being Shift.JIS and the other being EUC.JP. Shift.JIS is backwards compatible with 0201, but it has this funny feature where it just breaks fantastically if you try to interpret it with an ASCII interpreter, as opposed to EUC.JP, which works a bit better with ASCII interpreters, but is not backwards compatible with JIS 0201. And so there's a divide, and you end up seeing Shift.JIS take off on Windows and Macs, and EUC.JP take off on Unix systems. And this gets even crazier when you start to look at the cross-support of the individual character sets for each encoding standard. So obviously ASCII supports ASCII, JS X021 supports JS X021. Shift.js stops at 0208, and EUCJP supports 0213, but only when it's 3 bytes and not 2 bytes, which creates a bunch of really weird cases where there's a bunch of code expecting 2 bytes and they get 3. And so all of this confusion actually matters a lot in the story of Unicode because it inspires Unicode. So basically, Unicode, the idea behind Unicode largely comes from some developers, one of which being Mark Davis, who is a co-founder of the Unicode standard, who's working on the very first kanji Mac out in Sapporo. And while he's there, he's having a lot of trouble communicating with the Japanese developers because the Japanese developers speak a certain amount of English. He, as American, speaks absolutely no Japanese. And there is one person in the company that can fluently speak both, and they work in the marketing department. So they go back and forth, and this is a major problem of doing this translation. And again, it's really hard to move from like one encoding standard, which at the time might have been like Mac OS Roman, over to Shift.js, which is what they're using to build a kanji Mac. And he realizes there's seriously a need for just one universal standard, something that everyone can agree on and everyone can communicate in. And so eventually he ends up going back to the States and working with a group of like-minded people, as well as people around the world, and they end up eventually creating Unicode. And Unicode has this very kind of like lofty goal of enabling people all around the world to use computers in any language. And so far, it's actually been pretty good at that. It supports 135 scripts, it supports 1,100 languages, and 2,666 emoji. So the thing to think about Unicode is that we have to go back to those definitions that we defined back when we were talking about Morse code. There's 2 things we need to worry about. There's a character set, and then there's the encoding. The character set in Unicode is Unicode. That's all Unicode is. Unicode is a list of characters that are supported by Unicode. The encoding is the way that it's encoded. So the encoding in this case is UTF-8, UTF-16, UTF-32. This is the actual function that worries about translating that character set into bytes and then back out. So let's take a look at the humble Unicode snowman. So the humble Unicode snowman has, Unicode defines for him a name. They define for him a category. He's symbol other because he's one of those really old school Unicode emojis. And they define him a code point, which is a hex number, 2603. And when it really comes down to it, Unicode is just a series of code points. Every single character has its own number. And we've all just universally agreed that that 2603 means snowman. And that's all that really matters. The encodings will worry about that separately. Fonts will worry about that separately. Everyone has a separation of concerns, but the important thing is that there is a unique character called Snowman that is U203. Wait, U603. There we go. And if we look at how it's encoded in the 3 major encodings you've probably heard of for Unicode, UTF-8, UTF-16, UTF-32, they all end up different ways. UTF-8 is 3 bytes, UTF-16 is 2 bytes, and UTF-32 is 4 bytes. Now let's talk about why there are 3 encodings and how we actually ended up there, because it's actually quite interesting. So in the beginning, we decided, okay, there's probably 50,000 kanji out there. There's lots and lots and lots of kanjis. But realistically, there's not more than, like, say, 60,000 characters total. So we can probably fit everything inside of a 2-byte standard. And that becomes USC2, which eventually evolves into UTF-16. So the 2-byte standard is how we're going to do every single character. But quickly over time, we start to realize that to meet existing standards or be compatible with existing standards or based on other needs and that maybe there will be more characters, actually are more than 2 bytes. So UTF-16 is up in this way where most of the time, if you're within the multilingual, I don't know what's basic multilingual plane, then you're going to be a 2-byte character. That's most of the characters we need for communication. And then if you be slightly more than that, then, or a bigger character, then you split it up into two 2-byte characters, which ends up being 4 bytes. And this is what's called surrogate pairs. And you might have actually heard that term working with JSON before, and this is actually due to the fact that JSON is natively interpreted as JavaScript, and old JavaScript interpreters still think in this way. So it's still kind of relevant today. But so this is how UTF-16 works, and for the most part, it's okay. So we then decide when we need to go up, we're going to have, let's just do a 4-byte standard. So this is UTF-32. And this is really simple. So every single code point just defined itself in its 4-byte binary form. This was originally called USC4. But the problem with this is that it's a really big buy-in to ask from a lot of people whose data is already in ASCII, which is only 1 byte long. like that'd just be quadrupling the length of the code. Or even people whose code, all their kanji is in ship.js where it's only 2 bytes. So this is nice because it's like sound and simple, but it's really not that useful. And then we hit UTF-8, and UTF-8 is really the golden standard that makes compromise across all boards, sort of. So UTF-8, basically, with ASCII characters, they're going to be encoded as a single byte, which is a great trade-off for everyone who is still using ASCII. For the next set of characters being encoded as 2 bytes, and then for a larger set of characters, they'll be using 3 bytes, and then even the rest of the characters that are really out there, they're going to be working in 4 bytes. This is only the stuff outside of the basic multilingual plane. So if we look at how this works between the 4 standards, we have these 4 different characters. You can see the small Latin A encodes kind of in a very sane way between 8, 16, and 32, because it used to come from ASCII. The slightly fancier A gets encoded as 2 bytes in UTF-8, 2 bytes in UTF-16. With the poop emoji, the poop emoji ends up being an example of a surrogate pair. There's actually a great JavaScript developer out there who has this blog post that argues you should always do a poop test with your JavaScript. Put a poop emoji into your code so you know how you're doing surrogate pairs correctly. But there is an interesting case here, which is that kanji generally exists in this space where they're 2 bytes in UTF-16 and 3 bytes in UTF-8 because UTF-16 is more efficient. It's just a sequential, direct translation of that number into 2 bytes. And UTF-8 ends up spending additional bits to say that it's a 2 bytes or 3 byte character. And we will look at the way that UTF-8 actually works. You can see that there's additional bits that are set in the beginning of each one of these multi-byte characters to say how many bytes it's going to be or whether or not it's a continuing byte. But the important thing about UTF-8 is that ASCII is a direct subset of UTF-8. And this was an especially effective buy-in because anyone who had already written their code in ASCII or all their data in ASCII, they could just read it with UTF-8. And this is cool, but it leads to some interesting cases. So let's talk about Python. So in Python, there's 2 things you need to know. There's 2 types of strings. There are byte strings, which are a series of bytes, and then there are code pointer strings. So there's a series of code pointers. In Python 2.7, the way you create a series of code pointers is you put this little U prefix before it. You can see right here, you've got this U before this little snowman emoji, and that creates a Unicode snowman. And that is of type Unicode. And you can see that when you print out the string, it actually prints out the code pointer. That is the thing to keep in mind. This is just a sequence of code pointers, not bytes. In bytes, you would then convert it by doing a dot encode, which would encode it to UTF-8, or whatever encoding you want to use. And that then gives you bytes, which are represented with this \x. And then if you want to turn those bytes back in Unicode, you then do a dot decode. In Python 3, this is a little bit different. In Python 3, the string literal is just the Unicode string, as opposed to in Python 2.7, the string literal was bytes. And then if you want to encode it into bytes, you see this little B prefix, and this is now a byte string. And then if you want to decode it back, you do the same way. So this is the weird thing to get used to, is that the string literal means 2 different things between Python 3 and Python 2.7. But I think the thing to really wrap your head around here is just think of it as 2. Don't think of it as type string and type Unicode and type bytes and type string. The thing to think about is that I have a string of bytes, and I have a string of Unicode code pointers. And that there's an encode method that moves me from one to the other, and there's a decode method that moves from bytes back into Unicode. So let's go back to our original error message. So original error message was Unicode decode error, ASCII codec can't decode byte 0C3 in position 6, ordinal not in range 128. So what does this really mean? Unicode decode error. Okay, so I'm trying to decode something into Unicode. That's what a Unicode decode error is, trying to decode something. So I guess it's trying to decode some sort of bytes. ASCII is a way that I could decode bytes, so I guess we're trying to decode it as ASCII. 0C3, that's XC3, that's definitely not in ASCII. In fact, I'm pretty sure that's a 110 and then a bunch of other stuff. That sounds like it might be the beginning of a 2-byte UTF-8 character, and it's not in range 128. That makes sense because ASCII is only 128 characters. So let's talk about how you actually got here, though. So you just started a startup, and your startup's doing really well. It has open shop, it has some website. The website can accept users, and users are signing up for your really cool startup. And one day, the greatest thing that has ever happened happens. Jay-Z decides to join your startup. And so Jay-Z comes to your startup, and your code is really basic. You're like, okay, there's a new user, and the new user's name is Jay-Z. And you want to be cool, so you want to say hi to Jay-Z or any of your users in a really cool way. And you're like, welcome message. It's going to be like, hello, hello, friend. Welcome to my cool startup. But in place of cool, you're going to put a Unicode snowman because you know that Jay-Z is cool, and Jay-Z is going to totally understand. So what happens? It works. We encode the messages. So we have this Unicode string. We add Jay-Z's name to it. We encode the message as UTF-8. And we print out, welcome to my snowman startup, Jay-Z. And everyone's really happy. The next day, something really big happens, way bigger than Jay-Z. Beyonce decides to join your startup or create an account, also known as Beyonce. So Beyonce comes in, and immediately we see that the name coming in is in bytes. And we look at this, and it doesn't look like Jay-Z's name because these are UTF-8 encoded bytes now. And that's because it was always UTF-8 encoded bytes. The internet operates in UTF-8. So we got Beyonce's name, and there are these bytes that we wouldn't have normally seen when Jay-Z was there previously. And then we have the same message. We're going to try the exact same thing. We're going to say, hey, welcome to my cool startup. And then we see our error message. So, and then of course our exec team is really unhappy. So what happened here? Was the code that came in was bytes, or the data that came in was bytes, and the literal that we had was a Unicode string. And when we tried to combine those two, Python 2.7 was like, well, you know, I bet you actually want it to work in Unicode, so I'm going to automatically promote these bytes into Unicode, into a Unicode string. And of course, Python 2.7 decides that everything's probably ASCII, so it attempts to interpret it in ASCII, and then it fails. And this is where we see this error message. And you can actually see specifically which byte it was that triggers this, and this is why we're seeing this 0xC3, is it's the first part of that E in Beyonce's name. So ASCII cannot decode the byte right there. So this is this implicit promotion. And the weird thing about this is that your code was working previously, and now it's not. And this is why you're feeling pain, is because everything was running just fine, because UTF-8 is backwards compatible with ASCII, something that was written in the 1960s. So this is like really legacy stuff that's embedded deeply into your logic that's screwing you over. And if we look at what happens in Python 3, this is the difference. In Python 3, we never get past Jay-Z. In Python 3, we fail right away because Python 3 doesn't do any implicit promotion. It immediately identifies that this is a byte string and this is a Unicode string, and it raises this error message, which is way easier to read, which is just can't convert type bytes to type str, which is the Unicode string, the string of code pointers, implicitly. So Python 3 implicitly converts nothing. This is the biggest difference, at least to me, between Python 2.7 and Python 3. If you thought it was bad that string literals are different, this is really what's crazy, because you had code that used to work in Python 2.7 because you're always doing with ASCII data that all of a sudden just isn't working in Python 3. So now that you know how we got here, we're going to talk about a few best practices to keep you safe. Best practice number 1 is use Python 3. This should be the best practice of every talk at this conference. It's really hard to get around, and I realize that sometimes it's not a possibility, but it's really the one you should be going for because it just does handle things much better. If it's not, then you should be thinking like you're using Python 3 whenever you can. There's a function there's a special from future import string Unicode string literal. Use that thing. Pretend you're operating in Python 3. The second pro tip is to use a Unicode sandwich, and this is actually a Unicode sandwich. This is the Unicode character for sandwich, which is being added to Unicode 10. And that basically means that you should have bytes. There's bytes on the outside of the world, always on the wire, that are coming into your application, and they should be decoded when they enter and encoded when they leave. And the meat in the inside of the sandwich, those should be Unicode code pointers. And the third tip is always assume that Beyonce is a customer. So whenever you write a test, stop using your own name, stop using your dog's name, stop using your mom's name, use Beyonce's name, start putting weird characters into your code so you identify these issues way sooner. And that's all I got. Thank you.
Thank you very much, Devon. That was exactly 30 minutes. So unfortunately, we do not have time for Q&A, but we will have a 5-minute break for everybody just to do whatever they need to do. And yeah, in 5 minutes, we have the next talk. Thank you.